Welcome everyone to a new semester of TCS Plus, the original online seminar in theoretical computer science, committed to the carbon-free dissemination of ideas across the globe since 2013. Before introducing today's speaker, let me start with a few quick announcements. And in particular, let me start with a brief shout out to the other organizers, Clément Canon, Rachel Cummings, Anin Diadeh, Sumega Garg, Gautam Kamat, Ilya Rosenstein, Oded Regev, Tzil Shram, Noah Stevens-Davidovich, Thomas Vidik, and Eric Weingarten. Let me also mention that we already have another talk set up for 2 weeks from now by widetilde from the IAS and DIMAX, who will tell us about hardness versus randomness. But today, for our very first installment of the semester, we're lucky to have Merav from the Weizmann Institute tell us about one of the most recent breakthroughs in our most recent Best Paper awarded work on diameter reducing shortcuts and directed offsets. I'm really looking forward to this. So Merav, please take it away.
Thank you, David. It's really great to be here. I think since I've been introduced to TCS Plus, it was like my little dream to give a talk here. So I'm happy that I'm given the chance now. So I'm going to talk about diameter reducing shortcuts and offsets. And this is all a joint work with Shimon Kogan. Okay, so, it doesn't work. Okay, good. So please let me just ask you to be interactive as much as possible. Whenever you have a question, just ping me, okay? Okay, so throughout the talk, we are going to consider directed graphs. And now imagine that we wish to perform some type of computation on this directed graph. It can be single source reachability, shortest path, these kind of problems. In many computational settings, it can be PRAM, distributed, dynamic setting. The complexity of the computation depends on what we call the diameter of the graph, okay? Where we measure the diameter of the graph as the maximum U to V distance in the graph, and we take into account only UV pairs such that there is a path from U to V, okay? So if there is no path from U to V, we don't take it into account, and this is the diameter of the graph, okay? So it's very clear that the depth of the computation for computing single source shortest path depends on the longest path from S to every node that is reachable from S. So really our objective is to do the following. We wish to take the graph G and to augment it with few edges from the transitive closure of the graph. Okay, we call these edges shortcut edges, so that the diameter of the augmented graph G union H will be as small as possible. That will be our objective. And once we have that, we will perform our computation, such as reachability, on this augmented graph and enjoy the fact that it has a small diameter. Okay. So this brings us to the introduction of diameter reducing shortcuts. This notion was introduced by Ullmann, Yanakakis, and Thorup. And we say that a collection of edges from the transitive closure, TCG, is a D shortcut if the diameter of the augmented graph is at most D. And the interesting thing here is to study the trade-off between the number of edges that we add into our shortcut and the diameter that we obtain. Usually in the literature, we care about two types of shortcuts. Linear shortcuts, those that I'm allowed to add at most linear in N, number of vertices, number of edges, and matching shortcuts where I'm allowed to add something like roughly OM, O of the number of edges in the graph. The intuition behind this shortcut is that I'm adding not too much. The size of the graph is not increased by adding this number of shortcut edges. Okay. So now if you give me just 2 seconds and you ask me, okay, tell us something about shortcuts, this is probably what I would say. First thing is that the most trivial thing to do is to take all the edges of the transitive closure, right, into our shortcut set. This will bring us diameter of 1, right? But the size can be as large as n squared, which is like really bad trade-off. Then there is a well-known folklore algorithm that tells us the following. You can provide shortcut with roughly linear number of edges and bring down the diameter to square root n. We're also going to see formally how this folklore algorithm works. And then already in the first paper by Thorup that introduced this notion, Thorup conjectured that for every n vertex graph, one can compute linear size shortcut that brings down the diameter to roughly polylog. Okay. So Thorup also proved it for a narrow class of graphs like planar graphs, and it was open until SE came and he provided us with the first lower bound graph example. He showed a graph that has roughly m number of edges. The diameter of the graph was n to the 1/17. And in order to reduce the diameter of that graph, even just by 1 unit, you had to add superlinear number of edges, even superlinear in M. So that refutes Thorup conjecture. Okay, but luckily we have more than 2 seconds, so I can explain you now the history in more details. So the first algorithm by Weizmann and Yanakakis was kind of general. You give me the diameter that you want, d, little d, and I give you the number of edges that you need to add into the shortcuts. And the trade-off looked like that. If you give me a diameter of d, the size of the shortcut is n/d square. And we usually care about linear size shortcuts, and this is what you get when you set the diameter d to be roughly square root n. Then there was some follow-up work by Weizmann et al, and he shaved the log factor. It was not so easy to shave, so we appreciate that work. But other than that, no other trade-off, no other upper bound was known in the literature. So people kind of started to look into lower bound aspects of the problem. We mentioned SE, lower bound, and then we have lower bounds by Eng and Petty. And they showed, for example, that if you wish to add just linear number of edges, you cannot reduce the diameter to below n to the 1/6. Okay, so we had this tension with linear number of edges. You can provide diameter of square root n, but for sure you cannot reduce it to below n to the 1/6. Okay. And we also have some lower bounds for this matching shortcuts, and another exciting result by Louis et al from this very solver. So to get some warm up and get used to these shortcuts, let's just start with the folklore algorithm and see how we can get linear size shortcut with diameter of square root n. The idea is very simple. What we do, we sample a collection of square root n many vertices just by sampling every vertex independently with probability 1/square root n. Okay. And then we just add all the possible edges in the transitive closure between every pair of sampled nodes. So this is at most n many edges. And now, so the size analysis is clear, but the stretch argument is also kind of simple. What we need to do, we are now going to consider any u to v shortest path in the graph G. If its length is less than square root n, then we are fine and nothing to show. Other than that, we can just look at the square root n length prefix of the path, square root n length suffix of the path. And then with high probability, we have the event that the prefix contains a sampled node from S, but also the suffix. And luckily, we add this shortcut edge to the graph, and that provides us a directed path from U to V of length roughly square root n. So this is the simple algorithm that we had for linear size shortcuts and nothing else. Any questions so far? Okay. Okay, so linear shortcuts are really useful. If we look at the state-of-the-art bounds that we had for computing reachability and shortest path in any non-sequential setting of computation, parallel, distributed, dynamic, the state-of-the-art results are all based on some kind of shortcuts. And in recent years, there have been a collection of really amazing breakthrough results about how to implement this folklore algorithm that I just described efficiently in these computational settings, okay? But we had no different point in the trade-off. And people have asked whether it is possible to actually break the square root n barrier using still linear number of edges. And this is the main point of today's talk. It's not about the time that it takes us to compute the shortcuts, but rather on the combinatorial properties, that the combinatorial trade-off that we can provide. Okay. So here's our main result. Our main result is to provide a new linear size shortcut that reduces the diameter to n to the 1/3. Okay. And now, if you are still good with diameter of square root n, actually this can be achieved with sublinear number of edges. You no longer need to take roughly n many edges, you can take n to the 3/4 edges. So we have like linear regime, the sublinear regime, and more formally, this is like the new trade-off that we provide. The interesting threshold point is diameter being n to the 1/3, okay? If you give me a diameter that is below n to the 1/3, the size of the shortcuts is going to be superlinear. But once you allow to provide a diameter that is larger than n to the 1/3, it becomes sublinear, and in n to the 1/3, it is really linear. Okay, so this is how the function looks like, and it might be more instructive to look at that in comparison to the folklore algorithm. Okay, so here we have this schematic representation on that. On the x-axis, we have the diameter, and on the y-axis, we have the size of the shortcut. And the green curve provide us the folklore algorithm, right? It looks like n over d squared, okay? And now in our algorithm, we look at this curve of n to the 1/3. Below that, the size of the diameter is superlinear, okay? But it looks something like that, n over d squared, which is what we get from the folklore, times 1 over d. So it's strictly like better in that regime. And then once the diameter is larger than n to the 1/3, the size of the shortcut becomes sublinear, but again, you can see that is again strictly better than the folklore in the entire regime, but we kind of have like a phase transition in the function at that particular point. Any questions?
Is there any like intuitive reason why this like transition happens, I guess, or maybe you'll talk about that later?
So the intuition comes from the algorithm. The real algorithm is actually the one that provides us with this trade-off, with the superlinear regime, okay? So this is the first function that we got. We plug d being n to the 1/3, this is linear. And then to obtain the sublinear result, this is obtained by sampling. We subsample a subgraph and we apply the other algorithm in a black box manner. So in truth, there is like one core algorithm, which is the one that the superlinear regime, okay? But I don't have intuition whether it should be the right answer. This is like far from being clear. Okay, so we also have some lower bound, at least for the sublinear regime, okay? So we know from Hangen-Petty that if you allow linear number of edges, the diameter must be at least n to the 1/16. So we extend that to the sublinear regime, and it's instructive to look at like the following two parameters, where the diameter is n to the 1/3. Currently, the upper bound is n, but the lower bound that we have is n to the 4/5, okay? For square root n, we mentioned that we do have sublinear size, but the sublinear size that we get by the lower bound is still considerably smaller, okay? So in the entire regime, there is still a quite significant gap. Okay, so in the first part of the talk, I'll just present how to break the square root n barrier. We just focus on the linear size shortcut providing diameter of n to the 1/3. And in the second half of the talk, I talk about offsets, where we wish to reduce the shortest path diameter of the graph and not only the diameter of the graph. So now we turn into the algorithm. And our first starting observation is that at least from this point on, until I tell you stop thinking about it, we can think about our graph as a directed acyclic graph, as a DAG, okay? Why is that? Suppose I'm given a general graph and I'm asked to build a shortcut. What I can do first is to compute the strongly connected components of the graph, and then shortcut every strongly connected component to diameter of 2 just by taking a node and adding star edges coming and outgoing from that star node, okay? This just takes me linear number of edges. So this is very cheap. This is within my budget. From that point on, I can just consider the contracted graph, which is a DAG, obtained by contracting every strongly connected component, compute the shortcut for that contracted graph, and then go back and everything is good. So at least when I have a budget that is linear and above, I can just assume that my graph is a DAG. Okay. That would be very useful. If I forget, just ask me why, but I'm supposed to say at some point, okay, this is because this is a DAG. Okay, yeah, so this is the strongly connected component, and this is how we shortcut every strongly connected component to diameter of 2. And from that point on, we just assume that the graph is a DAG. Another tool, which is very useful, is the following. Suppose I need to compute a shortcut for a very simple DAG, which is just a path, okay? Then it's very simple just to add linear number of edges and bring the diameter down to 2, okay? So shortcutting path, it's a very easy task. How can we do that? Look at the path and pick the middle point on the path. And then just add edges from every vertex on the first half to the midpoint, and from the midpoint to every vertex on the second half, okay? So I'm just adding at that point linear number of edges. And you can already see that if I have two nodes, one in the first half and the other in the second half, their distance is now 2, right? Because they go through the midpoint. So I just continue recursively. I go again to the first half and to the second half, I pick the midpoint and I continue. And for every 2 nodes at the point that they got separated, this is the point where I provide them a path of length 2. And overall, the depth of this recursion is logarithmic, and I'm adding at most like p log p many edges. Okay. So this is a very important tool that if you just want to shortcut a directed path, this is like a well-known effect. It's sufficient just to add near linear number of edges. Okay. So with no further ado, we can present the algorithm. Okay. So what's the input? The input is a directed graph, and the output should be a shortcut set of linear size such that the diameter of the augmented graph is n to the 1/3. The algorithm is going to have 3 main steps. The first step, what we do is we compute a collection of directed paths. These paths are going to be vertex disjoint, and the length of each of them is going to be n to the 1/3, which is the diameter that we wish to achieve. A very important fact of this step is that this step is applied on the transitive closure of the graph. Okay, so the directed paths that we are going to compute now are not in G. They are computed in the transitive closure of the graph. And now I'm going to present a super lazy way to compute this path, okay? This is what we do. We look at the transitive closure and we look for a path, a D path of length n to the 1/3. We find one, we add it to collection, and we omit all the vertices from that path from the transitive closure. And we continue. We continue this way until what? Until the remaining transitive closure has no path of length n to the 1/3. Okay. So this is just the first step, computing the collection of at most n to the 2/3 many paths, because the length of every path is n to the 1/3 and the paths are vertex disjoint. Okay. So this is the path collection. The second step now uses the fact that shortcutting the D path is easy. So what we do, we compute these 2 shortcuts that we just described before for every path in that collection, and we take all of them. And this is very cheap because these are vertex disjoint directed paths, and the shortcuts are linear. So this is like an easy thing to do. We denote this set as H1. It will come into the game again very soon in the analysis. Okay, so this is like the first set of edges added to the shortcut set. Okay, and now come the third step. And the third step, it might be instructive to recall the folklore algorithm. In the folklore algorithm, we sample square root n many vertices, and then we connect every pair of sampled nodes. What we are going to do here is kind of asymmetric way of sampling. We have path, n to the 2/3 path that we computed in the first step, and we have vertices. We are going to subsample path, subsample vertices, and then connect every pair of path and vertex, okay? And this is the point where we gain in the size analysis, okay? So here it how it goes. We are going to subsample n to the 1/3 directed path and n to the 2/3 the vertices, just by taking every path in the path collection that we computed and sample it independently with probability 1 to the 1 n to the 1/3, and same goes to vertices, okay? So now I have this set P prime of sampled path and set V prime of sampled vertices. So you can see that I have the budget to add 1 edge from every sampled vertex to every sampled path. The question is which edge will I choose? And this is the edge that I denote as EVP, okay? So you look at the vertex V, some vertex that got sampled and a path P that got sampled, and you look at the path P for the first vertex that is reachable from V, and you add that edge. Okay. So what's the intuition for picking that edge? The intuition is that that edge captures the entire reachability relations from V to all the vertices on the path. Okay. If I give you that edge, okay, you no longer need to look at the transitive closure in order to see all the vertices on the path that are reachable from V, because I added the edge to the first one and that captures everything. So I can compress the reachability relation of a vertex and a collection of vertices on a path by just a single edge. I cannot do that if I'm given two paths, for example, but I can do it if I have just one vertex and a path. Okay, so this is schematically how it looks like. I have this is the collection of all the vertices, and the red ones are the ones that got sampled, and I have the collection of all the paths P that I computed in the first step, and the red ones are the ones that got sampled. And then I have the budget for every vertex to add just one edge for every sampled path. What edge would it be? The edge goes to the first reachable node on that path. Okay. So this is the entire algorithm. Okay, this is like the second step of edges H2 that I'm adding to the offset. And here is like a summary of the algorithm, but we'll use the summary also to do a size analysis along the way. Okay, so we have the first step, right? The first step is the computation of n to the 2/3 vertex disjoint path that we computed in a very lazy way, just one after the other until nothing is left in the transitive closure. And then we have this step 2 that we just take the two shortcuts of every path, but we know that every shortcut is of linear size and all the D paths are vertex disjoint. So this is just linear number of edges. I'm saying linear, but it's like nearly linear, okay? Polylogs are like omitted. And the last step is considered pairs of n to the 1/3 D path and n to the 2/3 vertices. We add one edge for every pair of a sampled vertex and a sampled path. So this is again roughly linear number of edges. Any questions so far?
So I have one question about the step 1. In the transitive closure, if U and V are reachable, so if V is reachable from U, then you have to direct the edge, right, in the transitive closure. But then if you want to find vertex disjoint path, I mean, I can't imagine how we do that, because every edge is reachable from, every 2 points reachable from each other, you had an edge already. So
yes,
are you
yes,
just
yes,
work randomly or something?
So that just happens in the first step, right? I mean, you start by just taking a path in the first step. This is not the shortest path, okay, right? I mean, you just look for a path in a transitive closure that is long, that is of length n to the 1/3. Then you omit all its vertices from the transitive closure. Already by that, this is like already like something else, right? And you continue. So yeah. Okay.
Yeah, Merav said she's okay with it being slow, right? You're okay with solving the record longest path, right? So.
Yeah. So actually, yeah, I'm going to touch upon this point in the computational part. Now we are omitting all the details about computation, but actually computing the longest path in a DAG, and our transitive closure is a DAG, can be done in linear time, like n squared. So it's not like a big scene. It's not super efficient, but it's like polynomial. Yeah. Okay. Thanks again for having a DAG. Yeah. Okay. So now let me sketch the not really sketch, but give you the high level idea of what we want to do in order to provide the diameter argument, and then we'll see how to achieve it. Okay. So recall that we have these two sets of shortcut edges. The first set, H1, this is the set that contains all the shortcut edges of each individual path in the collection, right? So now for the diameter argument, we are going to look at some UV shortest path, we call it Q, in the graph G union H1, okay? So it's not G union all the shortcut graph, all the shortcut edges, it's just the first set that I added, okay? And now I'm looking at this shortest path. If its length is less than n to the 1/3, we are happy, we are done. Otherwise, again, we are going to look at this roughly n to the 1/3 length prefix and suffix of the path. So let's start with the prefix. This is easy, right? We sample every vertex with probability n to the 1/3, 1 n to the 1/3, right? So that means that with high probability, the prefix contains at least one sampled vertex just by Chernoff. This is like the easy part, okay? Now I'm going to the suffix. What I would like to show you is that with high probability, if you look at the suffix, there's going to be at least one node that lies on a sampled path in P prime, okay? This no longer follows by Chernoff, even though, I mean, it might be the case, right, that if you look at that suffix, many of the vertices do not even belong to the vertex, to the path that I computed, or maybe many of them belong to the same path, right? Here I sample every individual path with some probability. Somehow I wish to show you that in that suffix, there are many representative paths, that this suffix intersects many of the paths that I computed in the first step, and to show that such exist. But suppose that such exist, I'm claiming that then the argument is done. Why? Because then I know that I added one edge from a sampled vertex Z to the first reachable vertex on that sampled path, okay? So maybe it's not W, maybe it's not the vertex that lies on the path, but there is the first one, maybe it's X, and then I have this particular edge, right, in my shortcut. This is in the second set of the shortcut edges, and then I'm getting just a path from U to Z using that edge and going over the suffix, and I'm getting a path of roughly n to the 1/3, okay? So it's really all about showing you that there is a vertex that lies on the suffix and on a sampled path, so that I can guarantee that such edge is ZPI is actually in the shortcut, okay? That will be the goal. Any questions? Good. So that will be shown by a sequence of like 3 little claims, okay? The first claim is that if I look at this path Q, okay, I'm claiming that it contains kind of very few vertices that are not on the path that I computed. How few? At most n to the 1/3. Why is that? So suppose I have more, and on that path I mark the vertices that are not covered by the path collection in red, okay? So every such thing corresponds to a path of length n to the 1/3 in the transitive closure that is remains because those vertices are uncovered. So this is in contradiction to the maximality of the path collection. I stopped adding to the path once there is nothing there, okay? And this is the point where it is important to apply the computation, not in the graph G, but rather in the transitive closure, okay? So from that point on, we kind of consider that most of the vertices on the D path belong to paths computed in the first step. The other one are like super negligible. Okay. The other property is the following. If now I look at the path Q, this U to V shortest path, I'm claiming that for every path P, not only sampled path, but every path P in the collection of computed path, it can have at most 3 many vertices on Q. Okay. So here comes the thing that we are considering the shortest path between U and V in the graph G union H1. H1 contains all the shortcut edges of the path P, okay? And this is a 2 shortcut. So I know that suppose I have like 4 many vertices on the U to V shortest path, that means that on that path, the distance between U prime and V prime is at least 3, but I know that it must be at most 2 because I added the shortcut edges between U prime and V prime, okay? And this is the point that it's actually important that this is the DAG. The fact that if I look at the original path, right, and I add the shortcut edges for the path P, I know that if U appears before V on that path, then they must appear in that order on any path where they both appear. There are no backward edges, okay? So this is a very important property that later on in the talk, I'm going to refer to that again, Okay, so that's great, because that means that I'm going to see very few representative vertices from each given path that the U to V shortest path intersects. Okay. So let's see where we stand. By claim 1, I know that there are very few vertices that do not lie on the path computed in the first step. So that means that most of the vertices on that suffix belong to path computed in the first step. But then claim 2 tells me that there is no overrepresentation for a given path. From every path, I'm going to see it must be many vertices, and that means that that suffix intersects many different paths in the path collection. And finally, I can use Chernoff and say, okay, so with high probability, I sampled at least 1. Okay, and this is exactly brings us to the point which we wanted to show. Okay, so I have at least 1 vertex W in that suffix. It lies on a sampled path, so I'm lucky to have this edge and obtained the short path. So that's really the entire argument. Yeah. I'll give you a second to digest and ask questions, maybe. Yeah, something? Okay, so far I kind of put computational aspect totally aside, but now maybe it's a good time to recap the algorithm, but actually put the glasses of, okay, we don't have much time to compute these structures. Let's start to look into efficiency aspects of this algorithm. So the heaviest part is really the first step. This is the step that we compute like tediously the path one after the other. And yeah, maybe it can be done in polynomial time, but not very fancy polynomial time. We wish to compute it faster. The second step is actually super fast, right? Because we can compute the linear size shortcut very efficiently. So this second step can be done in like super fast linear time. And then the last step, we are given this collection of n to the 1/3 directed path and n to the 2/3 vertices. And I just wish to compute this edge, EVP, the edge from V to the first reachable vertex on P. And well, the way that we can do it is just by doing some kind, treating every path as a source. And this is kind of taking n to the 1/3 times m. So the main bottleneck is currently step 1. Although if people are going to, overcome this barrier and at some point want to bring it to linear time, I imagine that step 3 is going to be really hard to handle as well. Okay, so let me just try to look at that step 1 in an isolated, clean way. What exactly is the computational problem that we need to handle here? So here is the key algorithmic challenge. What we wish to do is to compute a collection of paths, right? How many, n to the 2/3, that have the following property. I want this path to be vertex disjoint. This is very important because later on I'm going to shortcut every path. So it's important for the size analysis that these paths are vertex disjoint, right? So that I'll have the budget to shortcut every individual path. But then I wish that if I look at the transitive closure induced on what remains, on all the vertices, the uncovered vertices, those that are not covered by the path, the length of the longest path in what remains is at most n to the 1/3. Okay. And this is very important for the diameter argument, right? Because we looked at the path and we want to say most of the vertices there belong to the path that we computed in the first step. Okay. So this is like the requirement that we wish to have for this path collection. And the question is, how can we do it fast? At least faster than, the naive way that I've just showed. And it turns out that this can be done in n to the omega time. It's still not far from what we want, but it's better than the lazy way of computing it. And this is based on the notion of chain and anti-chain decomposition. So what is a chain? A chain is just a fancy way to say a directed path in a transitive closure, okay? And an anti-chain is a collection of vertices that are independent set in the transitive closure, And the notion of chain and anti-chain decomposition takes the transitive closure and it decomposes the vertices into two types. It provides you n to the 2/3 vertex disjoint chains, okay, which is kind of the path that we wish to have, right? And all other vertices that do not lie on the path, on the chains, they can be decomposed into n to the 1/3 anti-chains, n to the 1/3 sets. Each of them is an independent set in the transitive closure, okay? And the key observation is that this is like exactly, if you just take the chain part from the chain anti-chain decomposition, this is exactly this satisfies the properties that we wish to have for our path collection, okay? The chains are vertex disjoint, this is great. Their number is good, n to the 2/3. But then you can observe that if you look at every path, directed path, it can contain at most one vertex from every independent set class, okay? Right? Because if in a given path, all the vertices, right, are connected to each other, right? These are like a clique, undirected clique in the transitive closure. And therefore, if you look at a directed path, it can contain at most one vertex from every anti-chain class, and you have at most n to the 1/3. So there are going to be at most n to the 1/3 uncovered vertices on the directed path, which is exactly what we wish, okay? So this gives us an efficient way to compute this path collection. What you can do is first compute the transitive closure. This takes n to the omega time, and this is like the barrier of this step. And then you can just compute this chain anti-chain decomposition. We have efficient algorithm to do that at transient n² time due to Grandoni et al. And take the chain part of this decomposition. This is exactly the n to the 2/3 path that we are going to work on from that point on. Okay. So the key question here is whether, the key question is whether you can solve it in linear time, but at least to be less efficient, to be less ambitious, is first to ask whether you can break this barrier of the transitive closure computation, right? It looks like the entire computation is in the transitive closure. So the question is, how can you compute this path collection without computing explicitly the transitive closure? And we have a follow-up work in which we can actually compute the path collection in this time, which is roughly linear, but for dense graphs. Okay. And this, I won't talk too much about it. It just works by some kind of a reduction to a mean cost max flow problem. So you solve some flow instance, you decompose the flow into path, and this provides you the path collection that you wish to have. Any questions before we move on to directed offsets?
Sorry, quick question. So when you said independent set, you meant matroid independent set, not graph independent set, right?
It's independent set if you avoid directions of the edges, right? Like not two nodes are connected by an edge. In the
okay, so it is graph independent set.
Yeah. It is graph, but you look at it in the undirected way. Two vertices are dependent if there is an edge from U to V or from V to U. Good. Any other question? Okay, so far we discussed really how to reduce the unweighted diameter of the graph. And that really helps if you wish to compute reachability kind of problems, right? You reduce the diameter. But now consider any task that has to do with shortest path distances, okay? Then it is required not to reduce the diameter of the graph, but rather the weighted diameter of the graph or the shortest path diameter of the graph. And as we are going to see soon, also these structures suffer from the square root n barrier, which we now break, but not in the same way as we break it for the unweighted case, okay? So it's slightly more involved. So now we consider directed weighted graphs. And we are also going to consider the weighted transitive closure, where the weights on the transitive closure are just the shortest path distances. So there is an edge from U to V in the transitive closure, and the length, the weight of that edge is going to be the distance in G from U to V. Okay, so this is just the standard way to give the weights, okay? And now imagine that I wish to compute a shortest path, right? From S, from a single source to all the nodes. Even if the diameter of the graph is small, because of the weights, it might be the case that the number of hops on the S to V shortest path is going to be very large, right? So eventually, the complexity really depends on the shortest path, the number of hops on the shortest path of the vertices. And this brings us to the definition of bounded op distances, okay? So for a given parameter beta, okay, the bounded op distance between U and V is defined as follows. You look at all the U to V path with at most beta edges, okay? We call these edges hops, okay? You restrict attention only to that, and you take the shortest one. The length of the shortest one is the d beta G UV, okay? So you restrict attention only to path with at most beta edges, okay? So in this example, you can see that for beta being 2, the distance between U and V is 200, but in the true graph, their distance may be just 1, okay? So many times if you restrict attention to use only few very edges, the distance is very large. So what is our goal? Our goal is to augment G again with few weighted edges from the transitive closure, okay? So that you reduce the number of hops of the shortest path, okay? Now I want to add few edges from the transitive closure so that when I compute a single source shortest path tree, it will be sufficient to look up to depth beta. Maybe I lose something in the approximation. Maybe I would not report the true distances, but I still wish to restrict attention only to this bound diameter beta. So this is exactly formalized by this notion of 1 plus epsilon beta directed offsets, okay? So we have two parameters, epsilon that represent the stretch that we are going to suffer in the length of the shortest path, and beta, which is the op bound. So what is a directed offset? Is a collection, hopefully many edges from the weighted transitive closure that satisfies the following. If you look now at the distance in the augmented graph between U and V, but you restrict attention only to beta hops, the distance is very close to the true one, up to 1 plus epsilon stretch, okay? So once you look now at this augmented graph and you wish to compute now single source shortest path tree, you can restrict attention up to depth beta, and everything will work well up to 1 plus epsilon increase maybe in the length of the shortest path, okay? The definition is clear. So actually, if we look at the folklore algorithm that we mentioned before, that by adding linear number of edges, you bring the diameter down to, it's very easy to see that this way you can also preserve the distances exactly. When you have two sampled nodes, just add the weighted edge between these two nodes, okay? So this provides you one, because epsilon is like 0, 1 square root n offset of linear size. And this is like exact, right? The question is again, whether you can break this square root n barrier, at least when you introduce some 1 plus epsilon approximation. Okay, so again, we have new trade-offs for offsets. In particular, we can break the square root n barrier, but now it would not be for beta being n to the 1/3, it will be slightly larger. It will be for beta being n to the 2/5. I'll try to give intuition why this is harder, why the algorithm pays here more than we had in the unweighted case. And we can also go to the sublinear regime by having something that is larger than square root n. So the true trade-off looks like that. Here, the interesting transition point is not n to the 1/3, but rather n to the 1/4. So we have the main algorithm, which I'm going to highlight, which is this one, the red one, okay? this algorithm, if you plug beta being n to the 1/4, it would not provide you linear size shortcut. It will be superlinear n to the 5/4, okay? But then by using some sampling tricks, we also obtain this green regime. If you use this green regime with beta being n to the 2/5, you get a linear size. Okay? So you need to play. Again, you have this transition point, but it's not exactly at the point as it was before, because one particular obstacle that we have in the weighted case that we didn't have in the unweighted case. But at least we can provide a near linear size shortcut offset with beta, which is sub square root n. So in the time remains, I'll just try to give really a high level idea of the algorithm, especially for people that curious about this problem. I think this is like a nice point to look at. And the main obstacle is that now we can no longer assume that the graph is a DAG. And the reason is that the DAG reduction that I described before, it doesn't preserve the distances, okay? So I can no longer do this contraction and work on the contracted graph, right? So this is the main obstacle. If you give me a graph which is a DAG, we can match really the bounds for the offset as we have for the directed shortcuts. But the point is that now we have backward edges, which we didn't have before. Okay. So it will be most instructive to look at this threshold point, which is beta being n to the 1/4, right? And try to obtain 1 plus epsilon beta offset for this beta. And the size would not be linear, it will be that one. But then by sampling tricks, you can bring it out to linear and increasing beta to n to the 2/5, okay? But this is like the core algorithm of the construction. And the high level idea, it follows the same kind of 3 steps as we have for the unweighted shortcuts, but with more complications. So the first step, we compute a maximal collection, again, of vertex disjoint directed path. But now the length of every path is going to be n to the 1/4, which is like the diameter, the upper bound that we wish to obtain. But now it will also work in the weighted, sorry, it should be in the weighted transitive closure, not in the transitive closure. But now I'm not just looking for one arbitrary path in the transitive closure that has n to the 1/4 lengths, but rather it has to satisfy some nice property with respect to the shortest path distances, okay? For example, at any given point, we will have the guarantee that the path pi that I provide, if the endpoints are ui and vi, the length of the path is the shortest path between ui and vi in the graph G, okay? So that path is also a shortest path. It has the same shortest path distance as the true one in G, and there are additional properties related to the fact that we have to now report near shortest path, okay? So this is not just an arbitrary way to compute them one after the other, okay? But we find one by having some criteria, we omit it, and we continue until like we are done, and that's that. And this is how we obtain a collection of n to the 3/4 many vertex disjoint directed paths with some nice properties related to shortest path metric. And now comes the second step, okay? The second step before, say, take every path and just add a linear size shortcut because it's very easy to shortcut a directed path. But now this would not be sufficient because this is a DAG. Now I know that if I look at the path pi and the vertex v appears before u, it's not sufficient to add the shortcut edge from v to u. It might be the case that when I consider some shortest path, right, between x and y, on that particular path, u appears before v. So I need to take into account also backward distances. And instead, this is like hard for me to say because it's super wasteful, but instead of adding linear size shortcut, what we are going to do is to add the most naive quadratic size shortcut. We just look at every path, and for every 2 vertices u and v on that path, we add the weighted edge to their shortcut, Okay, so now the length would not be linear, it would be quadratic, and this is the point where we lose. This is the point where we lose because this is like the DAG penalty. We cannot assume that this is a DAG, so we have a quadratic way of shortcutting every individual path. Okay, so this is the second step. Again, shortcutting paths, but paying more than before. And then comes the third step, okay? So this is like the step that we like. We have like paths with nice properties. We have vertices. Let's subsample a collection of paths and subsamples a collection of vertices and just connect them. So this is still similar. I mean, we subsample with this probability. So we get roughly square root n many paths and n to the 2/3 many vertices. But now it will not be sufficient to add just one edge from a sampled vertex to a sampled path. Maybe I'm adding this edge between V to U1, but this is of super large weight. Maybe the edge from V to U2 is considerably cheaper, okay? So instead of adding just one edge from V to P, I'm using the fact that I only care for 1 plus epsilon approximation, and I'm going to add roughly log n many edges by applying the following rule. I'm looking at the first vertex on the path that is reachable from V. I'm adding this edge. And then I'm traversing the path and I'm looking for the first vertex for which this equality holds, that the distance from V to U1 is already too large, is larger than a 1 plus epsilon approximation than the distance from V to U2. So this is the point that I need to add another edge. Okay. So I would not capture the reachability by one edge, but I will capture approximate 1 plus epsilon approximate distances from V to all the vertices on P using roughly log n many edges. Okay, but this is still cheap. This is just, if instead of one, you add log n. Okay, and this is like the size analysis, at least I can convince you that this is the right size. The first step, as we say, we compute a collection of this many vertex disjoint directed paths with some nice properties that I didn't even mention. But then the second step, add this quadratic size shortcut for every path. But then the length of every path is n to the 1/4. So I'm adding square root n edges for each of the n to the 3/4 many paths. So this is the total number of edges. And then I'm subsampling square root n many paths and n to the 3/4 many vertices. And I'm adding roughly tilde1 many edges from every vertex to a path. And this is again, this bound that we had. So schematically, it has the same structure as the shortcut algorithm, right? But inside, the little details there are kind of different because of the introduction of the weights. And of course, step one is going to be considerably more involved, which I avoided. And I cannot really show you the true up-bound argument because I didn't really tell you how to compute the path, but at least I give you some taste favor of it, of what's going to happen. Again, you are going to look at the U to V shortest path in the graph G union H1. H1 always represent all the shortcut edges added for each individual path in the path collection, okay? You only take that. And you look at the prefix, the beta length prefix, the beta length suffix. And by Chernoff, you are happy because it eats one sampled vertex. Good. Okay. Now comes the suffix part. You wish to show, okay, that there's going to be at least one vertex that lies on a sampled path, okay? But that path has another nice property. Not only that it got sampled, the length of this path is at most epsilon times the distance between U and V. Okay, so that little part from Z to U is kind of epsilon addition to the two that you are going to add. Okay, and that guarantee is not that trivial to achieve, but also you wish to show that I have an edge from the sample node to some vertex Z. Maybe it's not to the vertex that lies on the path, but it's a good approximation to that. And then the final path is again from U to X, from X to Z, from Z to Y, etc. But because of these properties, that the length of the sampled path is good, and that the edge that you added has a close enough weight to the true weight from X to Y, you obtain this epsilon kind of approximation. Okay, So that really brings us to the end of the talk and mentions some open ends. There are like so many interesting open ends here. First, for shortcuts, yeah, I think that the most interesting gap is still the tension that we have for linear size shortcuts. We have an upper bound of n to the 1/3. Angel and Petty have this lower bound of n to the 1/6. It will be super great to have efficient constructions of these shortcuts in, well, in the sequential, but mostly in the distributed and parallel. Eventually, if you do that, it would mean that it will be possible, for example, to compute shortest path reachability, single source reachability in linear time and less than square root n depths. That will be like the holy grail question here. There is one structure for which we didn't break the square root n barrier, and this is the exact offset, okay? So only when we settle for 1 plus epsilon approximation, we can break it. But if you consider exact offsets, the folklore algorithm is still the best that we have. So it will be super interesting to try and handle that one too. Okay, thank you.
Thank you, Merav, for a great talk. Maybe open the floor for more questions.
I have a short question. You talked to us about running time for the algorithms you gave, but you said there's an auxiliary step for some of the other algorithms, some extra sampling. Is that easy? Is that linear time, or is that also maybe hard?
Which one? The last step?
For both of the algorithms, you just gave the running time for the linear size, or at least for the
yeah, right? That's a very good question. Yeah. So this will take us. This is actually very, in our follow-up work, we also have improved. We break the n to the omega time barrier in the entire regime, but once we go to the sublinear regime, it's no longer m plus n to the 3/2. I mean,
okay.
Yeah. It's definitely harder because of these sampling tricks, because the way that we obtain these sublinear shortcuts, super sublinear shortcuts, is by sampling tricks. We work on some net graph. We sample nodes and we produce another graph, and that by itself requires time. Yeah, it's a very good question. It's harder. Yeah.
Okay, thank you.
Yeah. But actually, even in the folklore algorithm that people have studied considerably, the linear time that was provided is only for that point of linear. Like, I'm not sure, even if you give me some d, I don't know, being n to the 3/4, and you ask me, okay, give me linear time to meet this folklore algorithm, to the best of my knowledge, I'm not sure that this can be done. At least it's not that easy to obtain it from the improvement that we had in recent years.
Sorry, I have a question.
Oh.
Do we know what happens if we want some sort of undirected connectivity shortcut?
So in the undirected case, you mean offsets or shortcuts? Because
no, not for distances, just for connectivity. So reachability, but in an undirected graph, like undirected connectivity. Then can you then get linear size?
But then in connectivity, you can just take one node, right, and connect it to all the nodes in its connected component.
Okay, so it's trivial.
Yeah. Yeah, but offsets are still very interesting in the undirected case, but there are great offsets of like 1 plus epsilon beta offsets for beta being, I don't know, super poly n to the little of 1 and of linear size. So the situation there is considerably better.
Thanks.
I also have a quick question. So Merav, the way you presented, great talk, by the way, thanks. So the way you presented the folklore algorithm and then your algorithm somehow almost pattern matched as a kind of, you know, nice generalization of the folklore algorithm. I mean, it's more involved than that, but somehow the way you presented it, okay, instead of just sampling, you know, vertices and connecting these, but sample vertices and paths, what's the next structure?
What's there?
What's the next structure? So okay, you're sampling vertices and vertices.
Yeah, there is a reason. There is a
paths.
reason. There is a reason why I'm presenting it this way, because for a long time we were trying to improve it by saying, let's just sample path, right? I mean, you enjoy path because there are fewer paths than vertices, right? This is the whole point, that you have only entered two-thirds many paths. And if I have some magic and I'm getting this path and I somehow can compress the reachability relation between two paths, then the situation would be amazing. The problem is that you can think of two-directed paths that in order to compress the reachability relation, you have to add linear number of edges between them to capture the reachability. Like if all the edges goes like that, you know, from the first vertex on the path to the first vertex on the other path, etc. So unless there are some magic way to build paths of special properties, if you just want to capture the reachability from one path to the other, from all the vertices on the first path to all the vertices on the second path, in the worst case, you just need to add linear number of edges, one edge per vertex on the path. And then you don't gain anything by shrinking into path. So I think I'm still presenting in this way, maybe because I have like, you know, wishful dream that maybe there is a smart way to build this kind of path, or at least, you know, to break the graph in some way and handle one part in this way and the other one will have this magic property. But for example, if this magic happens, the n to the 1/3 become n to the 1/4. Okay, so this is how far this magic can bring us. Yeah.
Great. So unless there are any other questions, maybe thank our speaker again. Thanks again, Merav.
Thank you.
And for all of you watching this on YouTube, see you again in 2 weeks, maybe.